We're really only interested in the history of the Earth, whose origin closely coincides with the origin of the solar system, 4.571, when round up to 4.6 billion years ago. But to put this into the broader context, we place the origin of the universe at 13.772 billion years ago with a Big Bang, expansion phase, formation of the galaxies and the stars, etc. Our solar system has been around for only about a third of that time, forming from the leftovers of a supernova explosion. At the center of a large cloud of debris, there's a new star, our Sun, and the inner planets, including the Earth, accreted out of the rocky debris orbiting the Sun. The 4.6 billion year history of the Earth is divided chronologically following the structure of a nested hierarchy. The largest unit, geologic eon, is broken into geologic eras. Eras are further broken down into periods, series, and stages. And the first eon is named the Hadean because of the hellish conditions that undoubtedly prevailed during this time, lasting until 4 billion years ago when the Archean begins. The late heavy bombardment lasted from 4.1 to 3.8 billion years ago, that is, encompassing the end of the Hadean as well as the start of the Archean. During this time, the remaining asteroids in the inner solar system would have been smashing into the inner planets and their moons at a very high frequency. Once we get past the late heavy bombardment, we're looking at a young planet with conditions that would have been reasonably conducive to life. And the evidence is strong that cellular life originated in the earliest Archean, if not before that. The oldest unequivocal evidence for cellular life takes the form of stromatolite fossils from the Strelley Pool Chert in Western Australia, dated at 3.48 billion years ago. Stromatolites are bacterial mats that accrete into small reef-like piles over a period of decades or centuries. And they're actually fairly common throughout the Archean. And even today, there are stromatolite-like structures forming in places like Shark Bay in Western Australia and even in the Great Salt Lake of Utah. But it's the Strelley Pool fossils that tell us that cellular life as we know it first originated on Earth no later than 3.5 billion years ago. Could have been earlier. There is some less unequivocal evidence of earlier life from Nuvuagituk in Greenland, and this includes microfossils as well as carbon smudges that are chemically suggestive of biologic origin. But for your lecture notes, we'll go with a standard recognition of the Strelley Pool stromatolites as the oldest fossils. The important point here is that we definitely have cellular life in the early Archean, beginning an evolutionary diversification of life that has gone on for the entire time since. Molecular oxygen, either as a component of the atmosphere or a dissolved gas in ocean water, was largely absent through the Archean, and this doesn't change until the transition to the Proterozoic eon at 2.5 billion years ago. The Archean lasted from 4.0 to 2.5 billion years ago, an overall duration of 1.5 billion years, and it was during this eon that we see the origin of life and irradiation, and by this I mean a striking diversification, of prokaryotic life, culminating with the origin of oxygenic photosynthesis, which ultimately brought the Archean to a close. It's the change caused by O2 produced by living cells that defines the end of the Archean and the start of the Proterozoic. Oxygenic photosynthesis is what we normally think of as photosynthesis as it's carried out by plants, but this is really a specific form of photosynthesis, differing from the other kinds in its release of O2 as an end product. This happens because H2O, water, is the electron donor. Now, it's entirely possible to have light energy driving metabolic processes. We would call this phototrophy, in which there's something else besides water providing the electrons, and this is likely to have existed before the oxygenic version. Photosynthetic life could have prevailed throughout the Archean, with oxygenic photosynthetic life coming into play only near the end of the eon. Up until this time, sunlight and carbon dioxide would have presumably been abundant to cellular life. Now, the third important ingredient needed for photosynthesis is the electrons that can be put onto carbon dioxide for the production of organic carbon. Electrons, however, were kind of hard to acquire. They had to be taken off of existing organic molecules or from natural chemicals that could be easily oxidized. The evolution of a photosystem of pigments capable of using water as the source of electrons was huge. Water was as abundant then as it is today, and the organisms using this new form of photosynthesis would have had tremendous success. The great oxygenation event, moving us from the Archean to the Proterozoic, resulted from this huge success of cells capable of oxygenic photosynthesis, and this was either a catastrophe or a game-changing opportunity for life. At the start of the Proterozoic, the O2 released by photosynthetic cells would have started off in solution in ocean water, and eventually it became liberated into the atmosphere. In the earliest days, the presence of O2 occurred in intermittent pulses, as evident from the occurrence of banded iron formations in oceanic sediments worldwide over a period from about 2.8 billion years ago to 1.9 billion years ago. We'll talk about these a little bit later, but they give us clear evidence for a substantial oxygen-centered change in atmospheric chemistry centered on the Archean Proterozoic break. Free oxygen, O2, is reactive with lots of things, including the organic molecules of which cells are made, and this aspect of its chemistry would have actually made it lethal to cellular life. Cells had to evolve mechanisms, first to tolerate the atmospheric oxygen and then to make use of it, and this could not have happened until after the Proterozoic had begun. Now, here are a couple of questions for you. Why must the origin of cellular life have preceded the origin of oxygenic photosynthesis? And while we're at it, why must the origin of oxygenic photosynthesis have preceded the origin of aerobic metabolism? That's the metabolism using oxygen in order to get more energy out of food. Now, I hope these questions were pretty easy for you. We can safely presume that the very first microbes capable of oxygenic photosynthesis were already cellular, and that the oxygenic form of photosynthesis was a relatively sophisticated innovation achieved only after hundreds of millions of years of other cells tinkering with various other forms of phototrophic metabolisms. The very first cellular organisms would not have been capable of oxygenic photosynthesis. This would have evolved later. Aerobic metabolism? Well, it's also a sophisticated adaptation to life in an O2 containing atmosphere. Using the oxygen for the benefit of cellular metabolism would have evolved only under conditions with O2 present. And in order to have enough atmospheric oxygen to drive natural selection favoring this evolution of aerobic metabolism, you would need to have an already established oxygenic photosynthesis as an important ecological driver in the biosphere. The evolution of aerobic metabolism in some bacteria eventually led to the endosymbiosis giving rise to the eukarya, the domain of life to which we belong. In the oceans, O2 changed the chemistry by oxidizing the iron, basically removing it from solution in the form of iron oxide. We talked about this briefly before with the formation of banded iron formations in rocks that were deposited as oceanic sediments during this time. In the atmosphere, a similar thing happened with methane, CH4. Reaction with O2 caused the methane's conversion into carbon dioxide, CO2. Now, both methane and carbon dioxide are greenhouse gases, but methane is roughly 30 times more potent as a heat-trapping gas relative to carbon dioxide. With the oxygen of atmospheric carbon in the form of methane gas into atmospheric CO2, the before-after comparison of thermal blanketing in the late Archean versus the early Proterozoic is really pretty enormous. You're basically taking the heavy blanket away and replacing it with a light sheet with 30 times less insulating capability. Taking this into account, together with a much cooler sun at the time, only about 70% of its present luminosity, it's easy to see how the great oxygenation event was a main driver, causing the Huronian, also known as the Makanyene glaciation, from 2.4 to 2.1 billion years ago. This means that for 300 million years, the Earth was pretty much a frozen ice ball. Similar icehouse events occur through much of the rest of the Proterozoic, even stretching into the Phanerozoic. This eon-long chill, combined possibly with other conditions like an unproductive anoxic oceanic system, put life's diversification largely on hold throughout the Proterozoic. It only snaps back into abundant activity near the end as things were thawing out. The end of the Proterozoic corresponds with the start of the Phanerozoic, 541 million years ago. You could call this the Proterozoic-Phanerozoic break, but we usually refer to these important landmarks by the named periods on either side. So the last period of the Proterozoic is the Ediacaran, and the first period of the Phanerozoic is the Cambrian, and hence this 541 million year ago landmark is commonly referred to as the Ediacaran-Cambrian boundary. This is also the first such event defined for us by the fossil record. The Ediacaran, which covered the last 94 million years of the Proterozoic, is a time in which there's actually a fairly extensive fossil record, but one that documents life forms that are largely different from those that first appear in the Cambrian and continue on throughout the Phanerozoic right up to the present. At 541 million years ago, there is a complete disappearance of the Ediacaran fauna. There's also a significant shift in the carbon isotope ratio, the negative 13C excursion, which is something that we typically see at mass extinction events. This narrative suggests that the Phanerozoic, the period of life as we know it, as shown to us by the fossil record, started with a mass extinction event that did away with previous dominant life forms. The Phanerozoic eon is divided into three eras. From 541 million years ago to 252 million years ago is the Paleozoic, which is made up of six periods: the Cambrian, Ordovician, Silurian, Devonian, Carboniferous, and Permian. The way that plants and changes in the continental configuration affected climate and global paleoecology during the Paleozoic era is a major narrative in this part of Bio 202, and it also impacts the evolution of animals, which we talk about in the next unit. The Paleozoic ends at 252 million years ago with the Great Dying, or the Permian-Triassic event, a mass extinction that caused the loss of as much as 96% of the Earth's biodiversity. It was clearly a cataclysmic time in life's history. The next era, the Mesozoic, starts at 252 million years ago with the Triassic period, followed by the Jurassic, and it ends up with the Cretaceous. The Mesozoic era is most often associated with the large dinosaurs like Apatosaurus and T-Rex, though it's during this time where we also see the origin of birds, mammals, and flowering plants. Another great big mass extinction event occurs at the end of the Cretaceous, 65.5 million years ago, and it seems clear that an impact of a large asteroid or comet was a major cause of this extinction. The large dinosaurs were wiped out of existence, leaving terrestrial habitats to be taken over by the little dinosaurs, that is, the birds, as well as mammals. The time since the end of the Cretaceous through to the present is the Cenozoic, which is comprised of the Paleogene, the Neogene, and the Quaternary. I didn't have space to even put the Quaternary on this picture. These are times that are really too recent to be of any concern to us now. The chronological context for the microbes portion of Unit 2 will be the Archean and the Proterozoic eons of the Precambrian. And when we get to the plants part of Unit 2, we'll be dwelling primarily in the Paleozoic and Mesozoic eras of the Phanerozoic.